How are we doing today? Good. Okay then. So we are here for our chapter 23. What are we going to learn about this chapter? This is about the transition elements and their coordination compounds. So in General Chemistry 1, we mainly focused on groups S and P blocks, or group 1 to 2 and then group 3 to 8. So those are main group elements. So in this session we're going to talk about the transition elements. Remember the D block elements when the D electrons are being filled up. So that is what we're going to focus on. Okay, so we will learn properties of the transition elements, inner transition elements. Remember the F block elements, they are the inner transition elements, coordination compounds, and the theoretical basis for the bonding and properties of complexes. Lots of fun stuff. Okay, so the transition elements. So what are these transition elements? So the D block and inner transition elements. So the D block elements. So remember, can anybody remember what is the name of this block? Groups 1 and 2, they are called S block elements. Remember we talk about that. This is all the S1 orbital is being filled up in group 1. This is S2 and this is going to be, what's the name of this block? P block element. Remember this is P1, P2, P3, P4, P5, P6. So those are the last electrons that's been filled up in this block. So this is your S block, P block, and this is the D block. We call it D block because the D electrons start filling up in this block. D1, D2, D3, D4, like that. Okay. So period 3 and period 4, we have D block elements. When you come to the period 5, over here, from 57 we start filling up F electrons. So we call them as either inner transition elements or F block elements. So since these elements are within transition elements, we call them as inner transition elements or the F block elements. Oops. Okay, so those are the F block elements. So in this session, we are going to talk about D block elements and F block elements. So transition metals, remember they are the D block elements. What are their properties? So they are, you can see even from the name, we call transition metals. So they are all metals. Okay. Whereas the main group elements, so if you take the main group elements, we have metals and non-metals both. Metals are the S block elements, and then the P block mainly they are non-metals. Okay, so they have both metals and non-metals. Many transition metal compounds, they are colored, colorful, and paramagnetic. What is paramagnetic? Paramagnetic means that when you have your electron configuration, you will have at least, okay, you will have unpaired electrons. When you have unpaired electrons, we call it as paramagnetic. And then if all the electrons are paired, we call them as diamagnetic. Okay, dia means two magnetic, para means one electron. Most main group ionic compounds are colorless and diamagnetic, and transition metal compounds are paramagnetic and they are colorful. Okay. Properties of transition metal compounds are related to the electron configuration of the metal ion. So this paramagnetic nature, colorful complexes, colorful metals, they all have to do with their electron configuration of the metal ion. So these are some of the transition metals. Period 4. Scandium, titanium, vanadium, chromium, manganese, not magnesium, manganese, iron, cobalt, nickel, copper, zinc, they all are metals. So electron configurations of transition metals and their ions. The d block elements have the general condensed electron ground state configuration. Remember the condensed electron configuration and the expanded configuration. So the condensed electron configuration is you write the noble gas prior to the element. After that NS2, N is the main period number. S always follows the main period number. Remember we have 7 periods in your periodic table. So S would be directly next to the period number NS2. When the d electrons are going to fill up, that's going to be n minus 1. For example, if the S value here is 5s2, your n minus 1 would be 4d. And this x means however many electrons in the d electron d shell, right? N equals 4 to 7. So here D starts filling up in the fourth period, fourth main period. But for the main period which is S, but the n minus 1 for the D it's going to be 3. Okay, so N is equal to 4 to 7. And x could be 1 to 10 x. Remember there are 5 d orbitals. Each orbital can hold up to 2 electrons. So 2 times 5 is 10. So d can go up to maximum 10 electrons, and this the n value would be 4 to 7. Okay. And then when you come to periods 6 and 7, we include the F sub level. How do you write the F level configuration? You write the noble gas prior to the F block element, noble gas. Main period NS2, S would be filled up. And then for the F block, it's going to be N minus 2. If N is going to be 6, for the S6 is 2, and then the F would be N minus 2, 6 minus 2, 4. 4F14 and N minus 1. N is, if N is 6, 6 minus 1 is 5. 5dx. So N could be 6 or 7. Transition metals generally form ions by losing the Ns electrons before the N minus 1 d electrons. You see here we have S electrons, you have F electrons and the d electrons. Now we are talking about the transition metals, which is going to be, these are transition metals. So you have S electrons and the d electrons. Normally, first electrons that is lost is the Ns electrons before they lose d electrons. Okay. Orbital occupancy of the period 4 transition metals. The number of unpaired electrons increases in the first half of the series and then decreases second half when pairing begins. Now this is scandium. Scandium electron configuration, noble gas prior to that, and then the 4s2, 3d1. So unpaired electrons 1. Now tell me, is scandium paramagnetic or diamagnetic? Scandium is paramagnetic because you have one unpaired electron. Titanium again, 4s2, 3d2. Remember, according to the Aufbau principle, which is the energy, how you filled it up based on the lower energy to the higher energy. And then the other one we learn about is the Hund's rule and the polar exclusion principle, that if before you start pairing up, if you have the degenerate orbitals, degenerate meaning that they have the same energy, first you have to singly occupy before you pair them up. So titanium would be 4s2, 3d2. Vanadium 4s2, 3d3. So there are 3 unpaired electrons, again paramagnetic. Chromium going to be 4s2, 3d4. But remember, having half filled orbital, d orbital is more stable than having 4 electrons. So what happens is when you come to chromium, one of the s electrons jump into this 5th level and become 4s1 3d5. We learn about this in General Chemistry 1 also. Okay, so there are 6 unpaired electrons in chromium. And then manganese is going to be 4s2 3d5, 5 unpaired electrons. Iron 4s2 3d6, and then cobalt going to be 4s2 3d7. So likewise it start pairing up, and then the number of unpaired electrons become less. And when you come to copper would be nickel. After nickel, copper is going to be 1 electron more, so we would expect that it should come here. But when the d electrons are completely filled, they get an additional stability. So the 4s2, one of the s electrons, jump into the 5th d orbital and become 3d10 and 4s1. So those are exceptions. Chromium and copper are exceptions which we learned in General Chemistry 1. Okay, and then when it comes to zinc, that's 4s2 3d10. Zinc doesn't have any unpaired electrons. Okay. Okay, so this is electron configuration for period 4 transition metals. Write condensed electron configurations for the following: zircon, vanadium, and molybdenum. Assume that transition elements in higher periods behave like those in period 4. How do we try to answer this question? First, we locate the element in the periodic table and count its position in the respective transition series. These elements are in period 4 and 5. So the general electron configuration is noble gas, since they are d electrons, Ns2, N-1, and the d electrons. For the ions, we recall that Ns electrons are generally lost first if you are trying to do an ion. But zircon is not an ion, so we can write as it is. But when you see vanadium 3+ means it has lost 3 electrons. So we have to first lose electrons from the s orbital. Okay. Zircon is the second element in the 4D series. So you have to locate your zircon in the periodic table. Okay. And then noble gas prior to zircon is krypton. So the zircon, so look up your periodic table. Zircon is in the 5th period, right? So when it comes to the zircon, it already filled up s electrons. So it should be 5s2, and then you count 4d1, 4d2 is where the zircon is located. Okay, so that's going to be its electron configuration. Now the vanadium. Look up your periodic table and find where the vanadium is, which is the 3rd element in the 3D series. So its configuration is given by the noble gas prior to vanadium is argon. It's in the 3D series. So argon, and then it comes in the 4s. You first filled up the 4s, so 4s2, then comes the 3d. In the d electrons, that's the 3rd element. So it's 3d3. Remember, it follows this configuration. Ns2, S is in the 4th period, 4s2, N-1, 4 minus 1 is 3d. So 3d, vanadium is the 3rd element, so 3d3. That is the vanadium, but we want to find out vanadium 3+. 3+ means it has lost 3 electrons. So when the 3 electrons are lost, first it loses from the s electrons. So then 2 s electrons would be gone, and then one of the d electrons will be gone. So then it would be argon 3d2, vanadium 3+. Loses the 4s electron first, then one of the 3d electrons. And then the molybdenum. Again, we first write the molybdenum itself, and then you go for the iron. So where is molybdenum? Locate molybdenum in the periodic table. It lies below chromium in group 6b6. Right below chromium is molybdenum. Remember, chromium is an exception because it is 4s1 3d5, because it's going to achieve half-filled d electron configuration. So having 5d, it has added stability, 5d electrons. We expect the same exception as for chromium. The configuration for molybdenum is therefore given by krypton is the element prior to molybdenum, noble gas. It would be 5s1 4d5, just like chromium. You see here chromium? Chromium is 4s1 3d5. Excuse me. And molybdenum is right below that. There would be 5s1 4d5. So now it's going to lose 3 electrons. So the s electrons would be lost. Formation of the molybdenum ion occurs by loss of the single 5s electron followed by 2 4d electrons. So this electron would be lost, and then the 4d5, so 2 more need to be gone, so they would be 4d3. So then the molybdenum ion would be krypton 4d3. Okay, that's how you would find the electron configuration for elements and ions in the transition metals. Trends across a period in the properties of transition metals. Across a period, the following trends are observed. Atomic size decreases at first, then remains relatively constant. Why? The d electrons fill inner orbitals, so they shield outer electrons very efficiently, and the 4s electrons are not pulled closer by the increasing nuclear charge. Right? So we have seen what happens in the d electrons. They are filling in the transition elements. D electrons are the ones that have been filled, and they are able to shield the outer electrons efficiently. And then the 4s electrons are a little bit further away from the nucleus, and they are not pulled closer by the increasing nuclear charge. So atomic size decrease first and then relatively constant. And then we also learn about the ionization energy. What is ionization energy? Energy that needs to remove an electron from a neutral element or any charged element. Okay, so the ionization energy also increases relatively little across the transition metals of a particular period. And electronegativity. Electronegativity is the ability of an element to attract electrons towards itself. Okay, so the electronegativities tend to increase slightly, then decrease across the transition metals in a given period. But in the main group elements, we have seen a significant change in the size of the metals, ionization energy, and the electronegativity. But for these transition elements, since the d orbitals are the ones being filled, the change is not much. So these are the 3 periodic properties. Atomic radius, you see it start decreasing at the beginning and then it just remains little constant. Electronegativity tend to increase. Remember, electronegativity for the main group elements also we had seen it keep increasing. And which one is the most electronegative element? It's fluorine, and the number is 4.0. Okay, so this is again slightly increasing, going from 0.8 to 2.8. Electronegativity increases, but not as significant as the main group elements. You can even see here iron, cobalt, nickel, they all have the similar electronegativity. And then the first ionization energy, meaning removal of the electron, first electron from the neutral atom. You can see 419, 590, 631 increases slightly because it gets harder and harder to remove an electron as going from metals to non-metals. Okay. Trends within a group in the properties of transition metals. Remember, the groups are the columns in your periodic table. Within a group, the trends also differ from those observed for main group elements. Atomic size increases from period 4 to 5, but not from period 5 to 6. In generally, we have seen in the main group elements, size increases as you go down the periodic table since we are adding one shell. Principal quantum number in number increases. Okay, but here atomic size increases from period 4 to 5 but not from 5 to 6. Period 6, element has 32 more protons than its preceding period 5 group members compared to a difference of 18 for main group elements. So going from one period to another one, in the main group elements there were 18 electron difference, but going from period 6 element has 32 more protons than its preceding period 5 group member. So there is a big difference. Okay, so there's not much of a difference from 5 to 6, period 5 to 6 in terms of the size. Okay, we'll talk about oxidation states in the next session.